Thank you very much for that introduction. It's a pleasure to be here this morning, and I'm really enjoying visiting New England in such a beautiful summer period that we have at the moment. I'm going to spend a few minutes setting the stage for the project that I've been working on. But first, I wanted to direct you to my website. You can see the URL at the top right of the screen. Some of the things I'll be discussing today can be found on my website under that smart irrigation box on the bottom left. As we heard from the previous speaker, in the Southeast, we tend to have a lot of precipitation over the year. But, But as is typical, the distribution is not what we like. So here I have some numbers from one of our irrigation research centers that the University of Georgia maintains in Southwest Georgia. And you can see that for the past few years, during the growing season, we've had quite a variability of rainfall. We need between 22 and 28 inches to grow a crop there, depending on the crop that we're growing. And so although we may have that amount of rain during the growing season, the distribution, of course, as you heard from the previous speaker, is not exactly what we expect and desire. So we have to use irrigation. And people are using irrigation for a number of reasons. In fact, in our part of the world now, it's very difficult for farmers to get bank loans if they don't have irrigation, because the banks see that as a form of risk mitigation. So irrigation has become an important part of the picture, not for just producing better yields, but for also the whole economic cycle there. So irrigation is growing at a tremendous pace in Georgia. Every time we have a good year, the farmers are investing immediately into new irrigation systems. This is a GIS map of center pivot irrigation systems in Georgia in 2006. Since then, we have had many more added. You can see the concentration of them is in the coastal plain. So there's a line that runs. See if I can get the mouse here to activate. There's a line that runs across the state from west to east, which we call the fall line. Above that, we have the Piedmont and the mountainous part of the state. And here's where we have our agricultural area. And the concentration of pivots increases in the southwest part of the state. And you can see the number of pivots that we have available now. This is a Google Earth image of the very southwest part of the state. I'll be focusing a lot of my discussion on the project today about the state. But you can see here, there are lots of circles in the landscape. So 85% of the agricultural land in this area is irrigated by pivots. So the pivot irrigation is really overwhelming. This area is also very contentious. You may have heard about the water wars. Larry Parsons from Florida here is smiling because he's the cause of all our water problems. There's a discussion this afternoon, actually, about the water wars in the U.S., but one of the big water wars in the Southeast takes place across the Apalachicola, Chattahoochee, Flint River basins. It's very contentious because we have 3 states involved that are all discussing and demanding more water for their states. So what's going on in a summary is that we have Metro Atlanta up here, which is consuming a lot of the water that flows in the Chattahoochee River. Chattahoochee River flows south and meets the Flint River in a man-made reservoir called Lake Seminole. The Flint River drains this dramatically intense agricultural area. And Florida complains that there's not enough water delivered during times of drought to the Apalachicola River, which comes out of Lake Seminole and feeds the very important oyster estuary in Apalachicola Bay. The state of Florida recently sued the state of Georgia in the Supreme Court. So this has been in litigation for 30 years now, and it's finally hit the Supreme Court. And Florida is complaining, and here's a picture of Governor Scott from Florida saying that Georgia is using water in 2 ways that is unfair. One, that Metro Atlanta is using too much water in the Chattahoochee, and that the farmers in the lower Flint, that area that I showed with all the pivots, are using too much for irrigation. That area is a pretty complicated area because it has a very, very productive aquifer, the Floridan aquifer, but the rivers and the aquifer are interconnected. So when you decrease the level of the aquifer, you decrease the flow in the rivers. And so although most of the withdrawals are from groundwater, they directly affect what's going on in the rivers and its tributaries. So my team at the University of Georgia has been looking at a number of ways we can help reduce the agricultural water footprint in this area. And we have quite a bit of experience with precision agriculture, which means addressing variability in the field and using technology and knowledge to optimize how you apply inputs. And we said, why not apply our experience that we've had over the years with precision agriculture to precision irrigation? And so there are a number of reasons why you want to apply precision irrigation, but the main thing is you want to optimize how you apply the water across the landscape. So areas that need more, get more. Areas that don't need as much, get less. And I'm going to show you some aerial shots of fields and to try and demonstrate to you exactly why precision irrigation can help us realize significant savings. So this is a typical center pivot field in the southwest part of Georgia. You can see it's a circle. What you'll notice, though, is that there are large chunks of this field that are not farmed, either because they're in wetlands or because they're just other types of non-farmed areas. So in this particular field, 37% of the land area is not farmed. With a conventional center pivot irrigation system, the whole area gets irrigated, right? So what we want to do is develop technology, or have developed technology, that allows farmers to turn off the sprinklers over the areas that are not farmed. I'm going to show you this animation here just to exemplify how the technology works. So watch as we go over this pond. Some of the sprinklers will turn off completely. Then when we go over a wet area that requires less water, we're applying lower rates. When we have an overlapping pivot, we turn off the sprinklers again. When we reach a sandy area, we apply a different rate. So what we're doing now is we're addressing the variability we find in the field. Again, this technology is called variable rate irrigation. This is something that my team developed at the University of Georgia about 10 years ago. It's now been commercialized. And I want to show you how the technology is implemented in the field. Essentially, when we want to change rates, we individually control the water coming out of the sprinklers. And so we have solenoid valves that are controlled with technology. And you can see here how the sprinklers are coming on and off. So if we want to reduce the rate to 50% of normal, we're cycling the sprinklers on 30 seconds, off 30 seconds. So this has been commercialized. The patent now has expired. And all the big irrigation companies are offering their own variable rate irrigation systems. So Valley, Rinke, all of them are providing some sort of technology. And we think this is ripe. So now it's very easy for farmers, if they're interested in investing in the technology, and if NRCS is interested in cost-sharing this, to apply variable rate irrigation and do on-off. But what I really think is where we can get some more savings is through agronomic VRI, which means changing the rates over the soils so that you're applying what you need over the soils that need them. So here's an example of a pivot that has VRI installed in it and is doing variable rate irrigation over the farmed land. What you see there are small grids. Each one of those grids can have a different application rate, but it's not really practical for us to have 360 or 700 application rates out there. So what we do is we group the field into uniform management areas, or relatively uniform management areas. So each of those colors represents a part of the field that has uniform soils or uniform water need requirements. And so then when we turn on our pivot and we're going across the field, we get, each one of those zones gets a uniform amount of water. And you can see here on the text on the slide that there are some significant savings to be had by optimizing the amount of water you add. So I can envision the condition where all you're doing is redistributing the water because you may have had too much here and not enough there. But in almost every case where we've studied this, there are some savings because generally parts of the field are over-irrigated. So what we want to do now is transition to a field project that I'm going to describe to you, where we are looking at how we can implement this on a large scale in the lower Flint River Basin of Georgia and allow the farmers there to realize significant water savings. This photograph shows you a field that's about 250 acres in size. It's in southwest Georgia. The white lines indicate the boundaries of irrigation management zones that we have developed in this field by measuring soil properties like soil electrical conductivity, also taking into account topography and other features that we can see in the field. And of course, the most important part is using the farmer's knowledge of the field. The yellow push pins indicate the locations of soil moisture sensors. So this is the critical part I think that's been lacking so far, is the ability to include a lot of soil moisture sensors in the field so that not only do we have a static agronomic map of what the soils look like, but we can get dynamic response during the growing season of what's going on in the field. That way we can use the data from the soil moisture sensors to actually drive how much water we're applying on these irrigation management zones. The soil moisture sensors that are commercially available, you saw an example from the previous speaker, are kind of cumbersome. They need cables. If you're looking for a wireless solution, they're very expensive. You're probably talking about $2,000 to $5,000 per location if you want telemetry and wireless transmission of data. So my team and I have developed an alternative approach to doing this. We've incorporated, as you see on the left side of the screen, 3 watermark sensors, which are cheap and readily available and have been on the market for decades, into a probe that can be easily installed. We have also developed an electronics package that allows us to transmit the information wirelessly. You can see that on the right-hand side, one of our nodes installed in the field. It has a whip antenna that's mounted on a spring. When field traffic goes across this, the antenna just bends over, and so there's no obstruction to tractors and sprayers and everything that want to go through the field. Here's a comparison of what ours looks like in comparison to commercially available sensors. You can see the big advantage of not having to drive around. Plus, ours is powered by 2 AA batteries, so we don't have a solar panel. What makes us so energy efficient is that we're using mesh networks as our way of transmitting information, so we can daisy chain our data and jump from point to point, as you can see in the schematic on the left. So we can use low power radios that can overcome terrain obstacles as well as requiring lower energy. Once the data gets to the gateway, we're using a cellular modem to transmit it back to, so the gateway is our base station. We're using a cellular modem to transmit that back to our website. So the data packet you see on the bottom is transmitted hourly from the base station back to our web server. At the moment, we have a couple of NRCS conservation innovation grants to demonstrate this technology. We've selected 10 fields. They're grouped in fives along important waterways in the lower Flint. These are ecologically sensitive waterways, so we're trying to see if implementing this technology will really have some effect on the water flowing through the streams. Here's a snapshot of our user interface, so all the participating producers can log in and look at their data in real time, and I'll show you some examples of their data. We've done some graphics this year to allow them to look at information a little more easily from their smartphones, which is really what they want to do. None of them want to go to a website at home. They want to be able to do this with their smartphone. So here you see the field with the irrigation management zones. All the gauges indicate the locations of nodes where we have soil moisture sensors. The gauge is color-coded, so here in the top left you can see this gauge that is showing 140 kilopascals of soil water tension, which is fairly dry conditions, indicating that the farmer should probably irrigate. You can see the needles also in the red area, indicating irrigation is probably necessary. I want to show you some soil water tension graphs from last year because I think this really illustrates why we should be doing variable rate irrigation. So these 4 graphs are from 4 nodes in the same field. Last year, this field was being irrigated uniformly all across the growing season. And what you see here on these graphs on the bottom axis is time. So all along the bottom axis is time. And then along the y-axis is soil water tension. So we have wet conditions at the bottom of the axis and dry conditions at the top. So in these 4 different nodes, you can see dramatically different soil moisture patterns during the growing season. And I'd like to show you the difference compare the differences between nodes 3 and 7 and 2 and 8. Nodes 3 and 7, if you could look over here, were in what the producer told us was the most productive part of the field, had the best soils, grew the best corn. These were the parts of the field that dried out the most, despite the amount of irrigation the producer was putting on. This indicates to us that the amount of water that was being put on this field was not optimally distributed. So we have areas of the field that are less productive getting more water than they need, and the areas that are most productive getting less water than they need. These dry peaks here that you see occurred when the corn was tasseling and filling, so there was definitely yield loss there. So the big step forward this year is that we are taking the soil water tension data and we're converting it directly to irrigation recommendations for each one of these management zones. And so you can see here on the bottom right of the screen how the soil water tension data is converted into amounts of water to apply. So the numbers indicate here on the bottom right how much water you would need to apply to each one of these zones if you wanted to bring it up to field capacity, which means field slope profile up without causing drainage out of it. So you can see that it's slightly different for each amount. This was in early May. The differences are much more striking now. I really should have gotten a snapshot from just a few days ago because the corn has grown to different sizes now, and so some areas are drying out much faster than others. And so this information will be now transmitted to the pivot controller, the VRI controller, wirelessly by cell modem. And so when the farmer goes to implement irrigation, to turn on the system, the pivot would be automatically engaged to apply water variably, showing these rates here. The final thing that we're doing is we're trying to incorporate high resolution, high accuracy precipitation forecasts into the information that's available to the farmers. And this is very important because if they know with some level of confidence that we're going to get a good rain in the next 2 or 3 days, they may be willing to put off an irrigation that would cost them $4,000 or $5,000 in pumping costs. And so we're working with two different approaches. One is we're working with IBM, which has this Deep Thunder project. IBM has set up a test case for us on a 100-kilometer grid in southwest Georgia where they are providing highly accurate forecasts for us, which we are in turn providing to the farmers. And we're also working with the Atmospheric Sciences Department at Georgia Tech to look at an alternative approach to doing that. So I think what the bottom line of this whole project is that, you know, we've got the technology in place now, I think, to make significant impact. What we don't really know is how significant this can be on the regional scale. And in fact, we're in the process now of developing one of the AFRI water cap proposals to see the effect of this kind of technology on a river basin scale. How effective can we be in making a significant impact on the water resources that are now in part of the litigation with the water wars? And that's the end of my presentation. I did want to show you this slide to show you that we have some interesting aspects to our research projects. We don't only see mice and deer in our fields, we also see some more interesting wildlife. And this was taken in one of the research fields where we have our sensors last year. Thank you.